Okay, so welcome everybody. We're very happy to have Sabin here, and he's working at the Center for Study for Existential Risk on topics of modeling evolution and collapse of societies. So we're all very excited to hear what he has to say, and the floor is yours.
Thank you very much for the invitation. I'm going to be talking a bit about how I've been approaching the topic of societal collapse and how I modeled it during my PhD and my current work. And I've gone through quite a few cases of historical collapse. Easter Island, the Maya, the Romans, the Chinese dynasties. And there are a few common threads in the modeling that I'd like to highlight. And my usual starting point is with how can you do this? How can you model the collapse of a society? When I first started my PhD, this was quite a almost untenable task. You don't know exactly where to start, because there's so many different aspects that could be relevant to the dynamics that you don't necessarily have a good grasp of it. And how do you link the data, all the qualitative insight, all the different dozens of books that have been written on any given society? And it's very puzzling. How do you tame all that complexity in all that detail? And the same problem was actually faced by humanity throughout its entire history in trying to understand anything. I took inspiration from physics, in that our first scientific success didn't come from any earthbound phenomena. It actually came when looking at a much larger scale. And this has an interesting effect, in that if you zoom out, you can see the forest for the trees. And this proved as a key strategy. The phenomena on Earth have two forces, mostly electromagnetism and gravity. And electromagnetism makes things very messy. But at this level of the solar system, it doesn't play such a significant role, whereas gravity does. And you can have a much simpler description of the dynamics, which is Kepler's laws and Newton's law of motion, Newton's law of gravitational attraction. And this is enough to give you a low dimensional effective description of the dynamics of the system. And here the scale was key, because it actually allowed you to simplify the description and gave you a much more easier time in handling the dynamics. And my inspiration was the same. What if we zoomed out and looked at the large aggregate scale over the long term at societal dynamics? Can we get regular predictive behavior similar like the solar system? Are there forces that act over the long term that prove dominant and give us a simplified description of what happens? Or is it hopeless? And I think I managed to find and validate partially one such mechanism. It's not my own, it was pre-existing in the literature, but I added the modeling aspect to it. And yeah, this is essentially the sort of starting perspective on how to approach the problem. And I'll just jump right into it, how the modeling looks like. First, the field sort of got rejuvenated by this paper back in '98 by two economists, Brander and Taylor, who did an economic type of model for Easter Island. And they put some utility maximization assumptions in there. And eventually what they got was a predator-prey model. And if you compare it to your archaeological record, it actually does a pretty bad job at fitting it. And this was my first attempt at making a model. And I basically improved upon that model, and I got a better result. The fit is noticeably better, and you could have a nice interpretation for the different variables, which I'll get to. So this is my first work, and I will model the population, the resources. I introduce this initial variable of wealth, or capital, as you might want to call it. And this is a nice system, and and uses the same calibration as the prior model. So, and does a much better fit of the data. Now, and here I highlighted the variable alpha, which is the extraction rate per capita of resources. And this plays a crucial role. The system undergoes a supercritical Hoof bifurcation, where it goes from a stable equilibrium fixed point to this limit cycle, with large oscillations. And at a certain threshold, this transition occurs. And yeah, you can analytically derive it, which is a bit messy. And I've included this here just to illustrate the fact that even a very simple model, an exact expression can be quite complex. And in any model where, or in reality, if you ever want to determine such a critical value, like for example, the tipping point for global temperatures, is it 2 degrees, is it 1.5? It's quite a formidable task. And the people on Easter Island wouldn't have necessarily known what value this would be at, because a high enough value can give you a good lifestyle, whereas too high, then you get degrade the environment a bit too fast, and it won't recover in line with your demographics. I did the same type of modeling for the Maya civilization, and here the data sets were different. They were separated like 50 years in terms of the different data sets. One was about monument building. The other one was about birth rates and population, so demographics. And the same model manages to reproduce both time series pretty well, with some simple mechanisms about specialization changes in the population. So some moved from sort of low intensity agriculture to high intensity agriculture. And then because you had this surplus of food, some could transition to monument building. And this was it was a fairly simple mechanism that does a good job at explaining fitting the historical data.
Sorry, can I ask a question?
Sure, sure.
Yeah, so I understand that for any data set, you can come up with a population dynamics model that fits this. I mean, you can do it. I mean, adding specific terms, etc. So is there any universality between the model you just showed and the one before of Easter Island, or you're just cooking up different models to fit?
That's an excellent question. Now I'll get to that in about 2 slides.
Okay.
So excellent question. Yeah, that's I know. Yeah, you can have a neural network or whatever and put a zillion parameters and have everything fit.
You can make the ordinary differential equation as complicated as you want to fit this.
Yeah. I know. I'll get to all of that.
Okay.
Yeah. So here the underlying phenomenon is the same. There's a Hoof bifurcation that occurs above a certain resource threshold, but beyond this, there's another thing. Both dynamical systems showed the same underlying feedback mechanisms. So the equation I chose, they're not just, let's say, black boxes. Each term is meaningful, each parameter is measurable, each was not calibrated for optimization, but taken from the archaeological literature. So all the models are full of meaning. So they're as far away from a black box as I could get them. And the relationships they posit between the different variables is the following. You have some population stock that produces certain resources, and from that they derive certain products or benefits like food, shelter, different monuments, and all those benefits tend to lead to further population increase. Population increase, though, tends to diminish the benefits faster. So the both dynamical systems reflect this relationship. The dynamical systems themselves have different functional forms in them, different equations, which are very plausible given the history of the different civilizations, but both broadly show the same type of relationships. And this feedback mechanism can be generalized. And there is a theory proposed by Joseph Tainter, which I formulated in a causal loop diagram and sort of generalized a bit and applied it to other historical cases as well. So you have some measure of societal complexity, and this is a very involved notion to explain. There are over 50 definitions and various aspects of complexity. But here, it's best to think of it as some sort of specialization organization at scale. So for example, population working in agricultural production, this would have to be organized and specialized in various regards to do this work and at adequate scale. So typically you'd look for some measure, some variable within the society with those characteristics. And this complexity is usually used, essentially a problem-solving tool. And the way the problems are solved is you extract resources, and from those you get certain returns, which, because of usually high initial return on investment, you further invest in complexity. But the complexity over time comes with costs. And this mechanism is also very nicely illustrated by the Roman Empire. There you had an army, which was a specialized, highly organized, large-scale endeavor, so complex, which was used to conquer territory, from which you could extract precious metals, taxation, slaves, an increased degree of legitimacy, and all of those benefits tended to lead to further investment in the army and the state apparatus. But the army comes with costs, so these would tend to diminish your returns over time. And with the Roman Empire, what happened was this positive reinforcing feedback loop manifested in the growth of the empire over 500 years. But at some point, the territorial expansion no longer proved beneficial or as profitable. And what they did to continue the expansion or the continued military campaigns, they're not so much the expansion because it wasn't expanding anymore, was to debase their currency. So they reduced the percentage of silver from the coins such that they could temporarily expand the monetary supply. And this allowed them to carry on the campaign for longer until inflation caught up, and then they had to debase again. At some point, the coins became worthless, and the empire couldn't finance its endeavors. So it started losing territory and eventually collapsed. And I made a model of this where this mechanism is captured. And here you see the land extent of the empire and also the debasements of the coins. And the model also includes the army size. So each of these three variables reflects one part of the feedback mechanism. So the army size is obviously the complexity of the army. The land extent is the resources. And the coin debasement is essentially a measure of the returns that they had over their history. So then the same general feedback mechanism is captured. And here the nature of the equilibrium is different. You don't have to change a parameter value to save the empire. What you need to do is actually reduce the stocks. And this is what they did. The empire split in around 400 AD. And essentially, this was a good measure, but it was taken too late. From my modeling, if they did the split around 200 years earlier, and also came with a fiscal reform of reducing the silver content by 50%, this would have likely stabilized the empire for much longer. And here I showed the optimal policy and what happens if it wasn't exactly optimal. You'd still get some oscillations, but essentially it could ensure much longer time span. And in a way, there are two main takeaway lessons from the modeling I've done. One is this feedback mechanism diagram, which gives you essentially a guide to finding a low dimensional effective description for the system. So you need to look for a few variables that capture some measure of social complexity, some type of resources they're using, and some notion of returns. And if you dig through and think about it long enough, eventually some equations that reflect these relationships would be a good candidate to describing the dynamics over time and fitting the data set, the time series. The second sort of lesson beyond this more qualitative aspect is the fact that there are different functional forms that can prove useful in describing the dynamics. So in the history of physics, over hundreds of years, we've accumulated various laws that describe different forces. So Newton's law of attraction, or Hooke's law, or various things that you use when doing mechanics. And those terms are not obvious. Like, it took us quite a long time to discover and become proficient in using and modeling all those different phenomena. And the same goes with population biology. So over the last century, various terms have been proposed to model the interaction of different species. So one is logistic growth, the other one is the law of max action, which you see in predator-prey models. But for human societies, these type of modeling contributions are lacking. So what my work does is provide a few candidates for thinking about these things, like the effect of wealth on birth rates, or how you could model agricultural extraction in ancient societies, or this change between specializations, or the effect of some inflation on other variables. So obviously there's nothing holy about these. It's just they work in a few cases, and they can form a toolkit that can be applicable in other cases. Also, economics can provide such insight. It's a bit questionable in terms of certain foundational assumptions, but it also offers some functional forms that could be of use, Cobb-Douglas type of production functions. And yeah, this is one thing that sort of needs to be built up over time, and it gives you a broader toolkit in trying to understand and model these. And it's basically the opposite of a black box type of approach. Each term is meaningful. You know what the parameters mean. You have an idea how to measure them, and this is very significant. And because you can get a meaningful, well-fitted model where essentially you know what's happening. Of course, that doesn't mean it's true, but it can be validated in a very deep way. Like, it's not just some optimization of some parameters in a let's say neural network or something where you don't know what's happening.
Sorry, can I ask a question?
Yeah, sure.
So when you say I can measure the parameter, you just mean I can fit the parameter?
No.
So you mean you can
go in the real world and actually get a measurement of what the birth rate was, or what there's this parameter D I included here, which is the average number of times you can exploit a soil until it depletes, and this was 7. I took it from agricultural measurements in the US in the 1960s. They had the table with this on a certain page. I found what would be the case for pretty good soil.
Mhm.
The actual, this is an overestimate because in the Yucatan, the soil quality is actually poorer. But I took this sort of as a with a margin of error, basically. So I took that value of 7, and I didn't do any fitting, any parameters. For some parameters, I did do a fit, but there were just a few, and it was just basically as a sanity check. It wasn't so much to uh, ensure that the model is at the local minimum in the parameter space.
But
But
how are you measuring parameters for Mayan civilization and Roman civilization? I mean, how you cannot go out and make the measurement now, right? So
well, they're already been made. Like people have been bothering with this for hundreds of years.
Sorry?
So there's a lot of data that is out there and things that
Okay.
have been estimated. So there one key aspect about the Roman Empire was you had to set up an effective length scale for it, and this what worked out pretty well in the model was the size of the Mediterranean. So you could take that size, or what you'd expect an empire around the sea of that size to be, and that set a pretty good estimate of the maximal extent you'd expect, because this facilitated the fastest travel in the empire. And then with a bit of fitting, that has a small adjustment. But as a first guess, it gives a very good point where you start the optimization. And if it doesn't end up too far away, then it makes sense.
Thanks.
So this is what I
Can
meant
I
about
ask
measuring.
can I also ask a related question to what
Sure.
Jay asked?
Sure.
So, I mean, now you have all these parameters and all these features, but how do you know they are enough? So how do you know you didn't leave out something which is very maybe important, which is not in the model? I mean, you never know, obviously, no? So that's kind of an unknown type of thing. But
Yeah, the modeling can. Sorry, yeah. Well, if you finish the question.
no, it seems to be a pretty difficult question. I mean,
Yeah, so this has to do with the nature of modeling itself. Modeling can never provide necessary bits because you never know what actually proves relevant in the long-term dynamic of the system, or at any scale. Actually, you just have sort of a intuition, and you come up with a hypothesis about how all these feedbacks and all these variables relate, and hopefully it fits the data that you have. And what you try to do is keep the complexity of the model at a minimum, such that the number of shots in the dark you make are as few as possible. Now, what is a necessary aspect in the model? This is very debatable, and historians and archaeologists would list you dozens. So this was the most common part of the review process when I received their feedback. Was yeah, they wanted to include the zillion other effects, which didn't actually have that good data available, but it was just kind of their own internal narrative in their head of what was happening. And you can do that, but again, it needs to be validated with data. And if the data doesn't allow you to increase the model complexity, then you should be I would be hesitant to do that. Furthermore, what the model can only do is give you sufficient structure to be able to reproduce the data you do have. So there's never any necessary part of it, let's say. It's just if as long as it fits the data and it forms this sort of coherent narrative where the variables make sense, the parameters can be calibrated meaningfully, and then you have a good proposal for a theory of what happened. And ultimately, it can only be a theory. You cannot, we don't know what actually happened. And different people can come up with different alternative explanations. But if a model is good, then what could happen is someone does a measurement of some other thing that was never known before. And then with a small extension of the model, you might keep all the previous fit and results and successes of the model, and then have a higher dimensional expansion of it, where you reproduce the additional data set. And this actually adds more credence that the structure you're building on is robust and well validated and a good foundation for further extensions. This is very much how it's been done in population biology and in physics. Like you have a good foundation and then you can build on that. Sometimes you need to throw out the foundation and go quantum or something, but this is about macroscopic phenomena, so such a deep revision is not always necessary. And now I'm going to go a bit through a guideline of how to tackle this complexity when you model the system. This is ultimately where it's at, where the main struggle. How do you put all these threads together in something that makes sense? The first point is you need to define the boundary of the model. What the type of models I used are essentially system dynamics models, ordinary differential equations, maybe partial differential equations, depending if you want spatial resolution or not. But typically what I've done to get to that vantage point where things might simplify, similar to the solar system, is I aim for the highest level of aggregation. And this meant using mean field models, where you have this well mixed assumption that the components of the system only interact meaningfully over the time scale you look at them. And for that, I also looked at the largest temporal horizon available. So this is basically from the beginning to the end of the serialization. And then there's a matter of considering the spatial boundaries. And here, there can be a natural choice. For Easter Island, it was obvious, because it was just an island. For the Romans, it was basically the Mediterranean basis. This is effectively the length scale they usually traveled. And similarly for the Yucatan Peninsula, there was essentially just one region of the Yucatan. There are several, but they all had very similar trajectories in their collapse. And I took sort of a representative territory. And otherwise, it was the patterns shown were pretty common throughout the different parts of the empire, of the civilization. Then for the Chinese dynasties, you basically consider again the maximum spatial extent they could reach. And there's some pretty good sort of geographical features that limit this. And the key thing is to consider the speed of travel. You want the system to be well mixed over the time span you look at it. So they don't necessarily have to travel too fast, but you want basically a meaningful expression of the different variables you look at throughout the entire scale, the entire scale of the model of the system. So then once you have the boundary set up, you need to account for all the possible details that can be relevant to the society in question. And for this, you look at the available data. Often enough, there's not that much in terms of various stocks and variables and parameters that you can possibly have. They're very evolved narratives about what happened, because you have these written records and people making all sorts of ideas of various aspects of the society. But again, this zooms in and out at different scales, a lot of these narrative descriptions. And what you want is to keep consistency in terms of the scale that you're modeling the system at. And if you're only looking at long term, it needs to be social phenomena that actually persist over the long term. And here, certain feedback mechanisms can prove more long-lasting than others. For example, this one I mentioned about the complexity and resources and various forms of embedded energy. This seems pretty robust over time. It seems to be a universal go-to mechanism for how societies function, at least over the very long term. And there are only, for example, the Roman Empire, this military conquest was the common policy throughout the entire span of the empire. Similarly, with these agricultural societies, the agricultural techniques they practice, they were the common thread throughout, irrespective of other cultural variations or trends. So it's important to pick out those elements. Equilibrium. Does it have oscillations? Is it just some transient behavior? What type of dynamical system you'd expect to show that? And this gives you some hint. Then you have these insights from population biology, where you can use different functional forms to represent the relationships. And again, this the larger the toolkit, the better. You can use insights from economics or also cloud dynamics, which is kind of the emerging field of what I've been trying to do. And interestingly, there's also machine learning, and this could be the most powerful. So there's one method I found called SIND, which stands for Sparse Identification of Dynamical Systems. Here there's a very neat technique where, for example, you can give the time series of a Lorentz attractor, and it's all chaotic and a mess. But what this method can do is look for this space of possible features in a model. So all the different types of terms that can contribute in equations, x squared and cubic terms and whatever order you think is relevant. And it does an exhaustive search, and not actually, it doesn't do exhaustive search. It uses a certain type of regularization that picks out the right contributing terms. So basically, you give this messy, chaotic series, even with noise, and by looking at the gradients, it can pick out which combination of variables actually proves most well fitted to the time series. And yeah, you recover basically the Lorenz's equations for that. And I did the same actually for the Roman Empire, though there the data is not particularly very high resolution, so you need to do some smoothing in some way. And then yeah, there are filters that you can use to generate gradients and all sorts of techniques. So and this can be quite powerful because it can basically give you the equations after you put the problem is you need to put a large enough feature space of possible terms, and these terms all have to be meaningful somehow. They have to be some division of some variables that make sense to be divided, or some addition or something, or some product that can prove has something to do with the dynamics of the system. It can't just be some put any function in there that does something. And building up this meaningful feature space is the challenge, and that's why I listed those terms at a certain point in the presentation, because you want those type of combinations that yield a good result. In population biology, people have been arguing what these type of meaningful terms would be for a very long time. With this field of cloud dynamics, not so much. But yeah, there's all sorts of things you can do to make life easier. And how I'm gonna more or less end is some modeling criteria. So you have a model, or you have several models, and you want to compare them. What do? So the first point is historical fit. Does the model actually reproduce our knowledge of what was happening on the island or not, or on what in the society or not? And this is a very obvious thing, but in the literature I looked at, this was rarely done. So for Easter Island, as I showed, the authors didn't really bother to reproduce what was at that time the best known reconstruction of the archaeological record. And this was pretty common actually in the economics literature. In some of our other societies, this was a priority, but the fit is not enough. even if it is done, which wasn't that often. You need some plausibility of the underlying assumptions. So even if an economic model can do a good fit, is it built on what we know about human behavior? Is it consistent with the sociological and psychological facts? Or you can't just make up, a story about something and then, I mean, yeah, you can make mathematical fiction as much as you want, but you want it to be as coherent and in tune with the rest of our knowledge as possible. Then there's a matter of the model structure, how you choose the variables, the equations, the parameters. All of them have to make sense in some regard. Sometimes it's hard to find just this addition of nonlinear terms might not be sufficient. Sometimes it might make sense to have a more involved expression, which just again, you can still see its sense, but again, these are also emergent phenomena. So even it might look a bit surprising, it doesn't necessarily have to be discarded. But again, if you keep it simple enough, then it's still reasonable in terms of the models that the model structure, and yeah, the parameters that you put in the model ideally should be calibrated in a way that's perfectly consistent with the system. So if the parameters that have been measured, it's good to be able to the model make a good fit with those parameters independent of any optimization. And again, if some parameters are very large or some are very small, this is a red flag, just as you'd have in a machine learning model. And also the equations themselves, some in the literature that I looked at had the division by zero, essentially at some points. The variable shouldn't have gone to zero, but it could definitely have some singularity in there, which is not really realistic when you think about it. So there's this aspect of some heuristic that makes sense, maybe using this toolkit that's been developing over time for different parts of the model. And there's a lot there, but it's a bit of a black art. You can't really, you can maybe write a guideline of how to do these things, but it's not, in physics is much more precise, let's say, when you're applying the Newton's laws or whatever you're doing to describe the system. The toolkit is much more robust and well tested. There's a good book called Complex Population Dynamics by Turchin that actually does have these little guidelines of guides of how to do this modeling for various biological systems. Then after you have all of this, there's the issue of how robust is the model. So if you change some of the parameters, is it gonna explode? Is it gonna fit any better? What's gonna happen? There was a model for the Maya civilization that tried to account for precipitation that was very actually sensitive to changes in parameter values. And this sensitivity is implausible realistically because I mean, you don't have a perfect measurement of everything in the model. And if a small change is going to perturb it, then it's likely not descriptive of the real system. And yeah, there's also error in the data. It's not noise, and you can't. The model should be robust enough to be able to any change in parameter values to stay within the error bounds of the data or the uncertainty of the data. And then there is the issue of diversity and flexibility. What sort of range of behavior can this model show? For Easter Island, there have been competing hypotheses about what happened on the island. One of them was that you had this ecocide narrative where they cut down all the trees and this paradoxical situation of the last person, what they thought about when they cut down the tree. There's another one where proposed more recently, where the society actually was very happy, eco-friendly, whatever, and well, it only was rats or some European contact that messed them up. And the model I proposed actually does show these two scenarios. It has the same feedback mechanism, the same model structure. You only need to change one parameter, and you can capture both narratives. Both narratives you'd think that show completely different underlying aspects of human behavior in relationship to the environment, but actually, in terms of the modeling and the feedbacks, they're the same. There's just one parameter value that was shifted, and that's it. So on most accounts, the two big camps on this would perfectly agree, except on one number. And that number, yeah, depends on certain psychological and sociological assumptions, but essentially that boils down to one thing, and it seems like a feeble debate. The moment you'd agree on these feedbacks and most of the system structure. Then there's the matter of how economical the model is. Does it have superfluous elements? And this is where all these presumably necessary parts of it can come into play, where you can have a very involved mental narrative of what was happening in the system. Then you might not necessarily be able to validate that with data, or all the elements that you have in your mind, qualitative aspects, might not necessarily be at the same sort of level of aggregation or let's say compatible in their timescales. So the phenomena might be operating at different levels, and yeah, you can make a multi-scale model of various sorts with different speeds in it. But again, you have to be mindful of those aspects, and you need good estimates of all the qualitative, all the quantitative possible descriptions of the qualitative aspects you have in mind. And it is very hard to go through and do a good job. It's possible, but again, you have to be mindful of all these elements. Then there is the issue of reproducibility and ease of communication. With an agent-based model, you'd have a much harder time because of all increased level of detail. With these mean field models, if you have an ODE, then it's pretty straightforward. Yeah, this is another thing to keep in mind because, for example, there was this one model, limits to growth, which was for modern society, which was actually too complex. Like it had so many assumptions in it that what they thought would be a necessary aspect to describe the world, that they didn't actually even bother to do historical fit. Like the fit was done like recently, like a decade ago, and it showed the model actually does a good job of reproducing some of the trends of the last 40 years. But again, the starting point of the limits to growth, for example, which is a very well-known model, were kind of flawed. Like they didn't do the historical fit, which is like the number one criteria to bother with. And secondly, they put these mental narratives before sort of empirically validated functional forms that prove useful in describing these emerging dynamics. And basically every graph from that paper, in terms of, they have a lot of these relationship between two variables that they try to, that the fit in if are there some multiplicative factors that serve to determine the birth rates or some other large-scale emergent effect. And all those tables and everything they included, all those basically required one publication independently to be validated. And just throwing that much detail in the model, like it's becomes untenable to validate and to have a meaningful debate. And what happened was most people misunderstood it. And now it's as useful as and as important it was to open a debate. It sadly lost steam because it didn't go through this long-winded process that physics and population biology went through, and even economics. But economics has a problem with the validation part. So this is the span of my work up to now. The 4 articles I've done on most of the data I found in the archaeological record. So for Easter Island, the Maya, the Romans, and the Chinese. And yeah, they're all open access. You can easily access them. And there will be a lot more to say. So this was a talk focused on the modeling part. There's a lot to say about complexity, the nature of it, how to think about it, how does this relate to biological systems. There is the issue of societal paradigms and how these apply to modern society. Then there's the why societies collapse and why don't they change their underlying dynamics fundamentally. This has to do with some costs. Then there is a structural demographic theory, which operates on a shorter time scale than the theory I am proposing. And there's also the issue of trauma and this emergent sociopathy that you can have when you have increased population pressure. So there's a lot I can unpack and expand upon. I have some extra slides, but I think we'll go for questions now.
Great.
Thank you.
Thanks, Sabin, for your talk. Quite nice. Let's open the floor then for questions. Jay has raised hands.
Yeah, just one question. So about the first slide you showed, you showed the Newtonian approximation to the planetary orbits. But you probably know that you can go even larger scale, and we have large scale simulations of the universe, for the large scale structure of the universe. And, it's magnetohydrodynamics that describes that coupled to gravity, etc. So you could also think, can we do a large scale simulation here? Because what you're showing is like specific individual populations or specific setups. And this was what population biologists were doing, in the 70s. Like, they focus on a group of rabbits or whatever. And now we have macroecology that we can actually simulate the whole planet, with still population dynamic models, but more complicated. And at the end of the day, we can see that, biodiversity is highest in the mountains, in the Everest and Latin America, etc. And we have the time evolution. So now, in principle, one could try to do something similar on the planet for civilizations and population dynamics of, human beings, right? Yeah. So do you have any, thoughts about that, or?
Yeah. So the complexity of the model needs to be earned. So you can't just throw the complexity gratuitously. Like this is how I think all these things that have to be in it. With the large-scale simulation of the universe, again, we had a century where we didn't have any computing power, really, to think about what makes sense maximally. Like what are the terms that makes the most sense? Because it's the Ricci scalar, that seems like a good option for it. But again, we had a long time to sort of filter and go through this, and the techniques and methods we use now, at least in physics, they're well merited. Like we got to that point because we can look and actually the system also allowed this. There's enough regularity in it that we can look deeper and deeper, and we can move beyond this type of modeling and do it much more at a finer scale. And this is essentially if you go to try to explain finer details, then you need something more than these mean field models, something like an agent-based model, essentially, or
I'm not talking about finer details. I'm talking about more coarser details, right? The length scales is higher, right? The universe simulation is at larger scales than at the scale of the planets, and the macroecology is bigger than the single population of rabbits.
Yes. But if you want to find the spatial patterns of how the galaxies are distributed and the matter is distributed, this is not the spatial scale. There is actually much smaller, because you want to.
You mean for corroboration?
yeah. I mean, you don't, you're not just interested, for example, in the average density of the universe, which would be an aggregate measure, right?
Mhm.
You want the how are things patched? What are the patches of matter? How they're distributed? What's the overall statistical ensemble it's part of, and the properties of this sort, which are much, which actually point to a finer scale of resolution
Mm.
at least spatially.
Mm.
Temporarily, yeah, you still want to look at over the entire thing, but you're focusing a bit more in terms of the spatial component. And
Mm.
this introduces additional complexity. Essentially, you need some sort of PDE, something to depending on the type of model you want to look at, that gives you the gradients throughout the universe or your system. And yeah, this is what people have been doing for migration. You need some spatial resolution there.
Right.
But you need more data as well. You need a lot more data because you want to capture the different patterns. So that comes, and the complexity is earned and merited because you do the measurements for the additional measurements for this spatial data. It's much more finer grained, so you deserve a more complex model. You need a more complex model. So yeah, that's some of there's more to say there, especially about these the universe and the different gravity models that you can have. You can actually get away with just two if you go to sort of a higher derivative theories of gravity. Like you only need two additional parameters to fit most the Fisher-Tropsch relationship for most the galaxy velocity, speed. That's where it breaks with the Einsteinian assumptions. So
Right.
yeah,
Yeah, I mean, yeah, that's a different discussion. Here, I'm more
yeah.
interested in how you can bring this to the same level as biodiversity research, in which exactly you do the kind of thing that you were just talking about, migration patterns and spatial resolutions. But I guess there is data on that, right? Because
Yeah.
yeah.
Yeah, there is data. It's also the mathematical methods you use to look at it through. Having dynamical systems, no different ordinary differential equations, partial differential equations. You want to look at gradients. You want to there's a specific focus and sort of calibration that the person going out in the field or the collecting data has. And if all people have only been trained to do linear regression and certain things, they would sort of focus on and design the strategies with that in the back of their mind. If you do it with the dynamical system back in the back of your mind, then you do maybe the data collection a bit differently or a bit more attuned to whatever description you made of the system prior. And this yeah, it's good to have a diversity of these things and maybe completely independence of the data collection. But it's I don't know, it's not an easy thing to tie in together. So all the information and all the models and all the insights, they need to coalesce and form a coherent story. And having all the data and the models, there this is usually the dialogue hasn't been very fluid in throughout the fairly short history of this field of cloud dynamics. So, and there's another issue of human psychology. So it's very hard to actually gain, and this is why I looked at the largest scale and at most aggregate level, because I was hoping to get traction. I was hoping to get a coherent narrative out of it. If you go to a smaller time scale or closer, for example, looking at Twitter data and how people interact, the time scales there are super short, and it's essentially like going from the low dimensional effective theory in physics to the standard model. The complexity of the interactions can explode, and because the time scales are much shorter, and there you need to account for psychological aspects, many more that need to be quantified and understood, each on their own basis, and it is a very sort of step-by-step process, and in a way it's not done in a necessarily coherent fashion throughout the scientific community. Because there are different paradigms, different ways, different mathematical approaches. The modeling is done, and harmonizing all of that takes a long time. For physics, this happened because nature was kind enough to give us nice, regular predictive patterns that we could sort of test and retest and re-measure as much as we wanted, and it always proved the same. With human behavior, this is much more turbulent. So yeah, and the equilibrium, the time to get to a sort of coherent theory is much longer. So
Thanks.
Thanks. Well, we have some questions in the room. Also, there was one question asked in the chat. So let me first go there, and then open questions in the room. So I'm interested in, Theo asks, I'm interested in hearing more about elite overproduction. How do you define elite? Is our current civilization moving towards this, since we already have a surplus of over-educated people?
this is this is going to sort of shorter time scales where more feedbacks become relevant, and the theory there that becomes important, I think, is the structural demographic theory that has to do with elite overproduction. The thing is with this, I actually have a slide on this, related to, it's not just elite overproduction, it's essentially overproduction in terms of all social roles. Because yeah, if you have too many people that want to do the, if you have a very large population and all the sort of even non-prestigious roles have been filled up, then you have an excess population that is kind of redundant in a way, and you have very high unemployment. So that also becomes important and a source of tension in the society. And in this regard, there was one experiment in the 70s that was done on a mice population, where they tried to make a utopia for mice. So provide them with all the space, all the food, all the amenities they needed, with no, like, as nice and as you can possibly get. And what you naively expect out of this setup was the population to grow, reach an equilibrium, and stay there. So just pretty much logistic growth of sorts. What happened was the population grew, and it didn't fill up the available space. It didn't present any sort of problem on any ecological basis, but eventually they all died. They grew old and died. And this was because they stopped reproducing. And the key aspect here was there are two actual carrying capacities. One is the ecological one, which was not even reached. There's only that 2/3 of the total available space. And another one was the, let's say, social carrying capacity, or social capital of sorts, which was also finite. So the number of possible roles that could be fulfilled in the society was limited, similar to the elite overproduction. But again, it's not limited to elites. It's basically all the roles and hierarchies in the society. And here, for the mice to engage in mating, the males had to give certain biological signaling for the females. And to do that, they first had to establish a dominance hierarchy. And to establish dominance hierarchy, they first had to compete and fight. And they did this. And usually when the losers would disperse out in the rest of the ecosystem. But because they were in enclosure, they kept on fighting. And there would always be contenders for the different social roles. And you'd have this not just elite overproduction, but general social role overproduction, that there were too many competitors for any given role. And this meant they were constantly fighting, and the dominance hierarchy was never established. And because of that, they couldn't get to the biological signaling that was necessary for mating, and hence they stopped reproducing. And eventually they all grew old and died. Furthermore, because of the very high stress levels, because of all the fighting, the females actually were very atrophied in their reproductive capacity. All the stress hormones they couldn't even get pregnant anymore. And what happened, they also took these mice out of this environment and put them in a healthy environment to see if they could adapt. And they couldn't. The trauma was permanent, and they could not be unlearned. So this has to do very much with structural demographic theory in elite overproduction, and what is a generalization of this. And it deals with it at all social levels. So it's not just elites. And this was the experiment with the mice, but the same could be argued could apply for modern society. There's this book called Bullshit Jobs, where not a lot work is being done, just appearances being kept, or you have very high unemployment, or you can have there's an argument to be made that after the Middle Ages, there was this very tumultuous, violent period, like the 7-Year War, the Napoleonic Wars. So pretty much after the Renaissance came this very violent period where agricultural production and was pretty much stable, but population increasing, and there was basically too many people for the available social roles, and we end up fighting. But this is one hypothesis to explain why you had this emergence of many different conflicts within that historical period. And then the Industrial Revolution tended to produce much more specializations. So this actually facilitated the relaxation of the system, because the more roles you had, the easier was to accommodate. And the same goes with the mice, actually. If you introduce play and creative activity in the society, for the mice, this increases the number of available social roles and alleviates some of these population pressures. But yeah, with us, it was just a matter of time that the Industrial Revolution could only provide so much different roles. Yeah, we'll be eventually facing the same dilemma. And also, this issue of declining birth rates in the modern world. The comparison with mice is limited in that, okay, we know there's some limited social capital that can be used up, and then needs to be replenished or expanded if you want to continue. If not, then you'd see some declining birth rates. And this is what we see in a lot of developed countries. But the mechanisms by which you get there are slightly different biologically than the mice. But it still has to do with this filling up of the different roles. And women no longer opting for motherhood that early, it's much more postponed or not at all. So there's a more involved discussion there to be had. But yeah, this is what I had to say about the elite overproduction and the different roles.
Thanks. There's another question from the Zoom. Mahan, you can just unmute and ask your question.
Okay. Can you guys hear me?
Yeah.
Okay, great. Thank you for the presentation. I was wondering whether you have come to the point of generating any recommendations for our current global or even national civilizations, or if you're aware of any good work that has been done, either based on your work or other work in literature for recommendations as to how to prevent basically civilization collapse.
The question, the big one. Can we save the modern world? Yeah, I had some additional graphs here with the mice where that show the population increase, and I have a model that shows this. I did a model of it. So what I'm doing is I'm building understanding of the dynamics of it, and if you understand the dynamics well enough, then you can figure out what are the leverage points where you can act upon and know what to do. And the problem with trying to solve this for modern society, it's trying to save it, is the same problem for all societies. It has to do with some costs and why the institutional reform is so slow. And for example, with climate change, we know we're killing ourselves in the long term, but we're still not changing. Why? And this is because of the very large return on investment that this type of infrastructure and energy sources gave us for the 20th century. Similar with the Romans, that the early conquests were very profitable, and all the institutions and paradigms and norms, everything was geared towards this military campaigning. Same with us with economic growth. Everything is geared towards that because this is what served us in the past, and it served us for 2 centuries. So it's hard to counter those effects. And basically, there's no real power structure that can really enforce or change this consciously. What can happen, the best that can happen, I think, is you have a partial collapse of the dysfunctional elements. For example, the 2008 financial crisis, that basically the financial system was too dumb to function. They did some stuff that it shouldn't. And that required a fundamental revision. And so certain countries did this revision, some others didn't. For example, Iceland, it took a completely different course than the US. And the moment each crisis happens and you have this partial collapse, this is an opportunity to redesign, because all that embedded power and legitimacy and whatever sort of merits and benefits it gave socially, those collapse and it proves itself unworthy. So you have a point where if you have the sort of wisdom, you can fundamentally redesign that part that's failing and gradually move to something else. So again, this requires a vision of what that something else could be. There's plenty of this actually for the US. Plenty of people have good ideas what to do after the banks failed. They were not listened to. Some other ideas were implemented, quantitative easing and this sort of stuff. And yeah, those are even bigger sunk costs that dominate. And sadly, they will also have to collapse at some point to be, and then you need to, there's these decision points when things break that you can start something new. But if you only try and implement and carry on with the past, then it's a recipe for failure. So this is what I would generally recommend. Build up sort of an alternative plan whenever crisis hits, such that when the system is redesigned, it's done in a way that serves the long term. And it's a very reasonable thing to do. It's just that it's a matter of actually doing it.
Okay, if I may, I have a few follow-up questions. Is there such a field as civilization engineering or like something that, no? Okay.
Well, I mean, it's essentially this trying to understand it's essentially cloud dynamics, but it has to do with just understanding the past. You have forms of social engineering, but this is more like has to do, I think, with indoctrination in various countries and various doctrines and stuff that are taught. So it's possible. It's just, yeah, it's not really in this, let's say, scientific realm as much as in political, I think.
Right. Right, because it feels like we have we've kind of started doing these things in like people who deal with forecasts or people who deal with like foresight and so on, but that maybe there's a need for an interdisciplinary field with people from complex dynamics or like complex systems, people who study historical trends, people who do forecasting, foresight, and then also in addition, engineering and entrepreneurs and these kinds of people who can maybe build platforms for coordinating and so on.
This is the problem with a lot of interdisciplinary studies. Most academic departments were built on this sort of silo type of every field has its own allocated part. And when you try to study emergent phenomena or something that has to do with interdisciplinary stuff, you need new institutions that don't have the same historical backing that the rest of them do. And it's harder to get funding, it's harder to get traction. It's starting now, it's the momentum building up, but it's still very early stages.
Okay, thank you very much.
Welcome.
Okay, so that's the need for deep action, the disciplinary institutes for study.
Yeah, this institute is very good in this regard, like the emergent phenomenon, like just exactly what.
Do I have more questions in the room for Sabin? Janusz, you want to ask something?
Yeah, just a quick question. I didn't see any stochastics here. So are there any, do you ever take fluctuations into account looking at SDEs, for example? Of course, that becomes analytically much harder, but sometimes they can be important.
Yes. So the issue of noise. The thing is with a lot of these systems, that has to do with some fundamental assumptions when you start the modeling. Because of the mean field, the large scale approach, the noise doesn't really appear at the century time scale. There might be fluctuations in populations, but they would be typically at, let's say, decade level. And for example, with the Romans, there was this one plague that affected them for around 15 years. But at the time scale of the empire, which is hundreds or 1,000 years, this only appears as a blip. So that would be the noise bit. But most of the demographic trends and the size of the army and general territorial expansion had to do with paradigms that were enforced beyond this, this disruption, temporary disruption of the system. So the stochastic elements are not so dominant in the long term, at least from the data was collected. There's not much evidence of noise at that time scale. This is the thing with I was looking for this force that dominates over the long term and proves predictive for the aggregate social dynamic. And you can have some perturbation, some level of noise, but it's not really significant to the overall trend. It's nowhere near that you need some statistical model to account for that. So it wasn't necessary, basically. There are other aspects that such a statistical or stochastic approach would be necessary. For example, I've also looked at warfare, and there you can build something like a Fokker-Planck equation that gives you the size of the different conflicts. But this is different work. It's on looking at different phenomena, not necessarily at the societal dynamic.
Thanks. So in your basic model that just captures this feedback loop that you explained, is the collapse, is that imminent? Is that like
No.
There always, or are there stable equilibrium solutions which you can arise at for some parameter values?
Yeah. So the diagram I had there allows for both behaviors. If what typically happens is you have the overdominance of the positive feedback group, so that gets in high gear for a very long time, and the other stabilizing counteracting feedback group isn't as strong. And eventually, when the resources get too scarce, then your society kind of cannibalizes and falls apart, just like the Romans did with the debasements of the coins. So they basically were taking up wealth from the rest of the society to finance the army. So this eventually led them to implode. But the dynamic, if the two feedback groups balance out, then it's fine. The system can equilibrate and there's no actual problem. And this was actually the case with the Maya. The Maya, if you look at the older historical record, before they started building monuments, they actually seemed to be in a stable equilibrium. And it was only at a certain point in their history that they wanted this building frenzy and started harvesting their environment much more intensely. And the same feedback mechanisms operate the same dynamical system. It's just there was this switch of parameters. But yeah, the conceptual quality of the scheme includes both possibilities. It doesn't exclude them.
So from that model, can you devise sort of a measure of the closeness to the collapse somehow, like in terms of values of certain parameters?
Well, if you build the model, then you can. The thing is, you need a good candidate for the different variables, for the measure of complexity, for the resources, and for the returns. And once you have a good candidates for those, you can see how the feedback operates, and then build the model and compare it with data and see what happens. The thing is finding good aggregate measure of complexity for modern society. And I did actually have a slide in some other presentation where I do this. The most adequate measure for us would probably be technology. because this is what we mostly use to extract the resources, and those resources then gives us our lifestyle, which is the main return, let's say, we have from all our activities. And our lifestyle is incomparable with any prior civilization. It's not even kings really enjoyed the level of comfort an ordinary person has nowadays in terms of possibility of travel, the type of exotic food that they can have. All these things we kind of take for granted now. It's they're quite historical anomaly, like enormously. And yeah, obviously all that lifestyle led us to further invest in technology and the way we go about tackling problems nowadays. And that's the reinforcing feedback, basically. But technology has costs, it has pollution, it has climate change. It might have all sorts of psychological ramifications, where it's not exactly community building in many regards, much more atomizing in various ways. So yeah, the same feedback applies, and more or less. It's just need to see those different variables and find ways to measure them.
Yeah.
Yeah. Well, this is a heavy topic in a way. Like there's a lot to think about, like a lot to process, and
yeah, a lot of things to take into account. Yeah, somehow also it's not super clear what kind of empire we're living in now, right? It's almost like a global civilization.
Oh yes. So this is a very important point actually that I didn't get to. So there's this one extra slide I had about the division of history. How do you go about modeling the system from this aggregate perspective, where you looked at what parts of it were well mixed, and depending on the speed of travel. And for the longest time, humanity was in the, I call it age of land, or the age of sparsity, where not much was happening because everyone was walking on foot. So it took a very long time for the system to be well mixed. And this happened until 3500 BC, more or less. This is when we domesticated horses and we started doing significant sea travel. And then came the age of sea, where most great empires emerged. And this was around for 5,000 years. And basically most major civilizations have a neighboring sea, which basically facilitated their growth and their expansion and their success. Basically these were like stable temporary macrostructures. So I also call it the age of stability for the different, this expanded period. And then comes the age of oceans. So basically each of these gives you the effective length scale of the you'd expect to find for the different society, given its complexity and speed of travel. So for land, you could go somewhere to 10 to up to 100 kilometers. With the age of sea, 100 to 1,000. With the age of oceans, from 1,000 to 10,000. So basically an order of magnitude increase every time. And the age of oceans, yeah, basically conquer the oceans. We have this period of discovery, age of discovery, and it's still ongoing. I also call it the age of saturation because there's the population levels. We reach those mice limitations, like that I mentioned, that you get these overproduction of all the roles. And this has been carrying on until the present day. And actually, the speed of the system has been increasing. The sales were only out of fashion in the late 19th century. And then the first flight obviously increased the speed of travel even more. And even more justifies the fact that the global system, this is the modern day society needs to be treated at the global level. So the system is well mixed in all regards. And yeah, it's very hard to basically make a prediction for a single country because you need to account for all the interactions it has with everyone else. So it makes sense to have the global model, like limits to growth did. And yeah, if you want this type of modeling I did, you'd have a big aggregate prediction for how these macro variables would change over time. But yeah, for individual countries, this is much more thorny because you need to account for every type of interaction. This is very difficult to quantify. Yeah, this is like my last extra slide.
Thanks.
Yeah.
Do you have any more questions, or thank the speaker again? That's it.